You know, from the thumping bass in your headphones to the crystal clear audio on a windy phone call, there's a kind of invisible engineer at work. Today, we're going to pull back the curtain on the powerful filtering technology that's constantly shaping the sounds of our digital world.
So, here's the game plan. First, we'll look at the everyday problems that these filters are built to solve. Then, we'll get into the difference between analog and digital signals, the raw material basically. After that, we'll meet the star of our show, the IIR filter, with its totally unique memory. We'll also uncover the clever trick engineers use to design them. And finally, we'll see why all this matters so much in the tech you use every single day. All right, so before we dive into all the technical stuff, let's ground this whole topic in reality. Because at the end of the day, signal processing is really all about solving problems that we all run into. I mean, have you ever really thought about what's actually happening when you slide that bass boost up on your music app? Or how your phone can just magically erase the sound of the wind so the person on the other end can actually hear you? Well, it's not magic. It's just some seriously clever engineering. And the answer is this incredible field called digital signal processing, or DSP. You can think of it as the art and science of being a digital sculptor. You take a signal, like audio, and you purposefully reshape it. The whole goal is to pull out the useful information, maybe enhance it, or get rid of the parts you don't want, like that annoying wind noise. But here's the thing. Before you can sculpt anything, you have to get the material into a language that computers can actually understand. And that means we have to jump from the analog world into the digital one. Think about it like this. Analog signals are these smooth, continuous waves, like a sound wave traveling through the air. It's how the world naturally works. But computers, they don't do smooth. They speak in numbers, so they need digital signals, which are basically just a series of snapshots or samples of that original analog wave taken at specific moments in time. And that simple conversion is the key that unlocks the whole world of digital signal processing. As soon as we have that string of numbers, we have this amazing digital toolbox that lets us completely reshape that signal. This is where the real fun begins. Now, inside that big DSP toolbox, there are all sorts of different tools. But one of the most powerful and one of the most efficient is a very special type of digital filter. This is the hero of our story today, the IIR filter. Digital filters really come in two main flavors. You've got FIR filters, which are pretty straightforward. Their output is based only on the input signal coming in. But IIR filters, they have a secret weapon, feedback. They're what we call recursive, which means their output is calculated using both the new input and a piece of their own previous outputs. This feedback loop is what gives them a kind of memory of what's already happened. And that's exactly where the name comes from, infinite impulse response. Because a little piece of the output is always being fed back into the next calculation, the effect of a single tiny input, an impulse, can ripple through the filter's output, theoretically, forever. It just keeps echoing. It's this infinite response that makes them so special. The best way to picture this is to think of an echo. A sound is made, that's the input, you hear it, right? But then a moment later, a fainter version bounces back. That's the feedback. This echo then mixes with any new sounds that happen. IIR filters are doing the exact same thing, just with streams of numbers millions of times a second. Okay, so this feedback loop is obviously super powerful, but it also sounds crazy complicated to design, right? How in the world do you build one of these things to do something specific, like boost the bass in a song? Well, it turns out engineers have a very, very clever shortcut. It's a huge challenge. You need a filter that does exactly what you want it to do, but it also has to be stable, which is a fancy way of saying that feedback loop can't spiral out of control and just create a useless screaming wall of noise. And here's the genius part. They almost never start from scratch. Long before we had powerful digital computers, engineers had perfected the art of designing incredibly sophisticated analog filters with circuits. We're talking decades of proven, stable, and reliable designs. So the trick is to just translate them into the digital world. The main tool for this translation is a mathematical process called the bilinear transformation. You can just think of it as a bridge, or maybe even a universal translator, between the analog and digital worlds. It takes the mathematical blueprint of a proven analog filter and systematically converts it into the blueprint for a digital IIR filter. So why is this method so popular? Well, there are two huge reasons. First, it guarantees stability. If you start with a stable analog design, you're absolutely guaranteed to get a stable digital one, period. Second, it prevents a really nasty type of distortion called aliasing. It's just a clean, reliable one-to-one translation. Now, nothing is perfect, right? There is one little catch. This translation process isn't perfectly linear. It actually warps the frequencies a little bit. It's kind of like looking into a funhouse mirror. Your reflection is distorted, but it's distorted in a consistent, predictable way. Engineers know exactly how this frequency warping works, so they can plan for it and adjust their design beforehand. Okay, so we know how they're designed, but why go through all this trouble with feedback loops and transformations in the first place? Well, it all boils down to one critical word: efficiency.
And this right here is the payoff. This is the whole point. Because of that feedback loop, that memory, IIR filters are unbelievably efficient. To get a really sharp, precise effect, an IIR filter can do the job with just a fraction of the computational power than an FIR filter would need. That means your phone can run complex audio processing in real time without totally destroying your battery. It's less processing power, less battery drain, and less memory being used.
And that incredible efficiency is why IIR filters are everywhere. They're the engine behind the equalizer in your music app. They're absolutely essential for the echo cancellation in your video calls. They play a huge role in modems. They're used to create musical effects like reverb. They are truly a cornerstone of our modern digital life.
You know, there's a line from our source material that just perfectly sums it all up. Signal processing is an operation designed for extracting, enhancing, storing, and transmitting useful information. And that's exactly what these filters are doing, working silently in the background to make our digital world clearer, better, and just more engaging.
So, the next time you adjust that EQ or make a perfectly clear call on a super windy day, you'll know about the elegant, memory-filled filter doing all the heavy lifting. It really gets you thinking, doesn't it? What other invisible processes are out there, quietly shaping our digital world?